So the topic is 3.5D printing. This image is an overview of the MIM and AM technical levels. In MIM production, generally the productivity is quite high, and above that, our micro-MIM technology satisfies the tight tolerance requirement, which is equivalent to machining. However, the starting up lead time is longer than machining since mold tooling is required. The mold tooling takes approximately 6 to 8 weeks and another 2-3 weeks for the MIM process. Therefore, the first sample of the mold comes out in 2 to 2.5 months. Importantly, after this about 2-month startup period, you will enjoy high productivity with uniformly well-controlled quality components. In AM production, generally it takes 2 to 3 days or even less, depending on the availability, to gain the actual green body sample if there is a well-trained operator and a well-designed 3D CAD file that suits our technology. However, for the serial production, such as 10,000 pieces or 100,000 pieces or more per month, is not really feasible for this technology yet. Then it's better to use MIM. So now we would like to introduce our new technology that is basically 3.5D printing, that is a fusion of MIM and AM. So it's a name that we created. So if you think we've never heard of it, that's normal. And you might feel strange about this 0.5, but we would like to provide you with advanced technology that defy the common understanding of both MIM and AM technology limitations. So our 3.5D printing technology will realize your ideal metal component design in minimum lead time with maximum powder metallurgy profits. We accept a small quantity with various design trials with AM technology, and without any technology gap, we will then transfer the metal parts design to the MIM serial production. So, since we have focused on small, complicated design, precise MIM production, none of the AM printing technology satisfied our requirement until we found Incus GmbH. So we may have another type of AM in our 3.5D printing technology in future. However, now we would like to introduce our latest. So I'm going to introduce Incus GmbH, the CEO, Dr. Gerald Mitter-Amskog.
Yeah, also from our side, a very warm welcome to this webinar. Thanks to micro-mim, thanks to Izumi Nakamura for inviting us to present Incus at this webinar. It's a really great honor for us to show what we're doing with lithography-based metal manufacturing. And we are very happy that we can call micro-mim in Japan one of our early adopters in this revolutionary technology. Yeah, just a few words about Incus, what we are doing and what we're up to. So basically, Incus, we are a technology provider for the additive manufacturing of metal materials. So we build the 3D printers, which you will see later on in the presentation, and we provide the respective materials for it. So in metal injection molding, you would call it the feedstock. We also call it feedstock, but in our case, the feedstock is a mixture of photopolymers, of a liquid resin with the metal powders inside of them. So it's similar to a metal feedstock, but a little bit different chemistry. And with our lithography-based printer, we print the green parts layer by layer. We built the printer in-house here in Vienna, and also we make the feedstocks, the metal feedstocks also here in Vienna as well. So we have experts along the whole value chain. At the moment, we are 15 people, starting from mechanical engineering, process development, chemical engineering, and of course, from material science. And maybe some of you know the company Lithos. They are involved in the lithography-based printing of ceramic materials. We are spin out from them. So basically the idea of Incus came about 4.5 or 5 years ago when we had a research project with Lithos when we printed metal materials. And then we decided, nah, it doesn't work so well with the Lithos technology. We need to make a new technology out of it. And then in September 2019, we decided to found Incus as a new spin-off or as a new company dealing solely with the metal printing technology. And to some of you who is more involved in the additive manufacturing world, we are also a proud member of AM Ventures, and they are a really, I would say, renowned investor in this field. So that's quite a nice quality sign for us. To my person, I mentioned it before, I was 4 years part of Lithos in the metal printing division, but before that I was involved in the lithography-based printing of ceramic materials, and before that I did my PhD at the Vienna University of Technologies, also dealing with the lithography-based printing of dental ceramics, mostly for crowns and caps. Yeah, so let's just jump to the technology, our lithography-based metal manufacturing process. How is it looking? So on the right side, you see the machine setup. So basically, to those who know a little bit the ways around additive manufacturing, our method is characterized as wet photopolymerization method. So as I mentioned before, we have this liquid starting material. So I hope you can see my pointer as well. On the left side, on the material piston, we have the starting material, our starting feedstock, and with the heated coating plate, we provide a fresh layer of material on building side of it. And then after the recoating process, we polymerize with a projector unit or with a really industrial projector unit, the so-called the feedstock, and print layer by layer this so-called green part. So the special thing about our feedstock is that it is solid at room temperature. It's like Play-Doh, or it has a butter-like consistency at room temperature. And the plate, the coating plate, is heated to roughly 40 to 50 degrees Celsius. And therefore we liquefy the material and always make sure we spread a nice uniform layer on the building side of things. And as the building piston moves down layer by layer, that's typical for additive manufacturing, for a layer-wise printing process, the material piston moves up and provides new material for our printing process. So as you see here, so we start with the printer, we create this so-called green part. The green part is still consisting of a roughly 45 volume% photopolymer, so a polymeric binder, and 55 volume% metallic powder. And so the printing is basically only the first step of this whole processing chain. So we need the binding and sintering step to really fully densify the part, but I will get to that later. But for this, we are very happy that we have this, that we have an experienced partner such as micro-mim on our hands to help us develop the debinding and sintering as well. But we will get to that a little bit later on. So what's the specialty about our process? With the highly homogeneous coating mechanism, because we have this the metal powder always in a binder system, we have a very homogeneous coating itself, very homogeneous spreading of the powder, and together with the high industrial or high resolution light projector unit, we can achieve resolution and surface aesthetics which are unmatched for additive manufacturing. So those are just the, I would say, we are using the general benefits of lithography-based printing for the first time also for metal-based materials. So I explained to you a little bit the production process in an actual application or for an application. So here at Incus, I would say we are the experts for getting, let's say, from the idea, from the general CAD drawing to a so-called, to the printed part, to the green part. We will see the printing process and the extraction of the green parts later on in the video. But here, for the steps on the right, for the post-processing, so for the thermal debinding and sintering, and of course for the necessary polishing or post-treatment steps, we highly rely on partners at the moment. So here, this is where we always are happy to cooperate with experienced partners. So let's take a look at the printing process. So this is what you're seeing right now is a look into our standard machine, the HAMR 35. You see the building area or the building platform on the right. So here on our laboratory scale machine, we have here 90 times 56 millimeters in X and Y. So this is the current resolution we can achieve. And on the left side here is the material chamber. And as the printing piston moves down, the material piston moves up. So this is a real-time video of the printing process. It doesn't get more exciting than this. And what you see now here on the building field, that is the polymerization of the layer. So on top of it, we have this industrial light projector unit with 35 micrometer resolution in X and Y. And after every coating step, we do this polymerization of a single layer. The polymerization happens all at once. It's not a laser-based system. Maybe some of you know when you do a laser polymerization or a laser melting process, you need to really write the single images or the single sections of the parts. In this case, we really polymerize the whole image at once. And if you do it correctly, and if the printing process works out well, you get really, you see printed green parts, which have the unmatched resolution and surface aesthetics for additive manufacturing. But we will take a look at the next printing steps later on. So if you allow me to go back to the to this sketch again. So during the printing process, all the green parts itself are supported in our butter-like feedstock system. So we don't need any support structures or connections to connect the green parts to the printing platform. So as indicated here, all of the green parts are supported by the feedstock, and we need this so-called decaking or extraction steps to get the green parts out of from the butter-like feedstock system. And this is what I would like to show you next. So after the printing process we have just seen in the machine, we end up with a block of feedstock, and you can see the block of feedstock, and we melt the surrounding feedstock, and this is how we extract the green parts. So here you see just the extraction of a few demo parts from our side. So in front of us there are some anvils, so demo structures, and in the back you see the St. Stephen's Cathedral. So this is, let me run it again. So this is basically the process, how it looks like in a nutshell. So this melting of the remaining feedstock is done with a commercial hairdryer. Basically, the melting point of the material is roughly 30-35 degrees Celsius. Yeah, and this is a kind of unique process. So all the material that is melted here, that runs through this net, you can put back into the printing system and reuse it. So this is how you extract the green parts from after the printing process. The big benefit on our side again is that if you compare it to a powder-based process, such as, let's say, if you're familiar with binder jetting or laser powder bed fusion, you always have a powder which is able to fly around or create some powder dust. In our case, everything is bonded with the feedstock material and can be reused in the printing process. So this is a relatively nice and clean, easy processing step. So, and if you do the cleaning right, you really end up with nice green parts that have this unmatched, I would say, resolution and surface aesthetics. In this case, or what you have seen before in the video, that was 316L stainless steel, and the parts have been printed with 25 micrometer resolution in the Z direction. So in X and Y, we have 35 micrometer resolution given by the projector unit. And in the Z direction, you can basically adjust the printing process according to your powder needs. The printing of the green part, I would say, is the most easiest step in this whole production chain, as you can see up there. So this is kind of an old part we printed with the University of Pforzheim, or with the company MedShape. You see the direct comparison between the printed green part and the final sintered part. So in this case, we used a material that had a solid loading of 50 volume percent. So 50 volume percent is binder, 50 volume percent is metal powder. And if you really go to close to 100% density, then of course you have a 50% volumetric shrinkage. And this is also kind of similar to what for instance, micro-mim is used to in metal injection molding there. The sintering is also comes along with volumetric shrinkage, and this is something, of course, you need to calculate into your design of the parts. Of course, the easiest way is to upscale the part, of course, but sometimes it's also involved that you need to simulate the shrinkage behavior of the parts, because you have always the influence of gravity, as you could imagine. The material at sintering point, for instance, 316L, you sinter at about 1,300 degrees Celsius. The material gets kind of really almost not really liquid, but kind of plastic, and then it can deform due to gravity. So overhanging structures, we don't need any supports to print overhangs, but it would be beneficial, always depending on the geometry, to use ceramic sintering setters or use printed sintering supports, which you could also potentially do with our technology as well. So that's why I want to emphasize again, if you're looking into sinter-based additive manufacturing, such as binder jetting or fused filament fabrication, it's not only, it's only debinding and sintering. The debinding and sintering typically takes also a lot of development work, and takes a lot of, it's also involved with, I would say, learning curve. And of course, this learning curve takes some investment from your side as well. But if you can do it well, you really get some nice applications, and this is what I want to focus on the next few slides. So here, all of the parts I'm going to show you are without surface treatment, so the surface quality is as sintered in this case. And here we can start with this one already. You see it was printed in this standing orientation, so that was the set direction of the printing process itself. And here you see the 35 micron resolution of the projector unit on the surface of the part, and also you see it a little bit visible here on the edges. So once again, this should show that you can achieve the highest resolution in terms of additive manufacturing for metal materials. Also, what I always like to compare is like this part. This is a part of a cell phone or a SIM card holder, and you see also the untreated surface, and you see the comparison of the texture of the glove compared to the texture of the untreated texture of the part itself. So I would say the lithography-based technology has this really unique feature when it comes to small and complex parts, and this is where I see this unique, I would say, benefit, or this complementary benefit for micro-MIM, because we have seen the really small and complicated, delicate parts before. This is where we're just unmatched in terms of resolution and surface aesthetics. What is also a very nice application for us, dental brackets. You could, as shown on the right-hand side of the picture, you could print them in all different forms and according to your needs. So in this case, we didn't need any sintering supports to support this, I would say, this knob on the outside, because the influence is gravity. Is when it comes to really small parts, gravity doesn't really have a big influence on the sintering properties. Then the sintering forces are kind of higher compared to the gravitational forces, and that makes the sintering, I would say, of small and complex parts also a little bit more easy. One thing that's worth mentioning here on those parts is that the surface aesthetics and the resolution in our process independent of part size. So you would get the same surface aesthetic and part size on, let's say, on those small dental brackets, but also on the larger drill head I've shown before. And also it's more or less independent of the orientation of the surface in the build platform. If you're familiar with powder bed fusion process, there's this large dependency on which inclination did you print the part. And for us, this is not so much the case. Here is an application we are using internally. So this is basically a holder of an internal sensor of the machine. So I think this is a holder of a temperature and humidity sensor of our printing chamber. So here, this is what happens if you let the engineers play around with the design. As you can see, this one was heavily designed to have a uniform wall thickness. So basically, you can print any green part, but the binding and sintering, the success highly depends on the design of your part as well. But once again, this is the same is true for any sinter-based additive manufacturing technology. And of course, to some extent, of course, for metal injection molding as well. Let's take a look at our HAMR 35, our series additive manufacturing machine at the moment. So in the video, you've basically seen a close look into the printing chamber of the machine. So we don't need to take too much time on that. The machine, the Lab 35, is intended for, I would say, a small scale production and material development. So this is really a good introduction to get used to the printing process itself. And of course, by 2022, by the end of next year, we are launching our next upscaled version, the HAMR Pro, to really lower the cost per part, make a more efficient printing process, but also not only enable more parts, but also allow the printing of bigger parts. So here we are aiming for a building field of roughly 200 times 200 millimeters. But you're not, we are not only focusing on the green part production, because this is, as I mentioned before, this is just the first step of this whole production chain. You really need to be careful and look all at the downstream processes as well. For us, in our case, that's the melting of or the extraction of the green parts from the feedstock block. Then you need the cleaning of the green parts, and then you, of course, you need the binding and sintering. So to really make sure you get a good production process, you need to consider this whole production workflow. Yeah, about the materials, we have most experience in steel-based alloys, in this case stainless steel, but with other customers, with development partners, we are working on copper, tungsten carbide, cobalt, titanium 6-4. So with those materials, basically we have shown that the printing process works in general. Because if the physical characteristics of the powder are quite similar, for instance, for the stainless steel you've seen before, we're using a +5, -22 micron powder. If we have a similar powder size distribution and I would say also spherical particles in, let's say, for copper powder, then we can quite easily print this and create green parts. The bigger challenge, once again, with different materials, is the binding and sintering, especially if you think about reactive materials such as titanium 6-4 or titanium alloys in general, or aluminum alloys. Those materials are quite reactive at higher temperatures. Because for us, this is, I would say, one downside of our process. We have a relatively high binder amount, and you really need to make sure to get rid of all the photopolymer binder system to avoid the formation of carbide. So roughly 450 degrees Celsius, the binder burns off. And if you go too fast during the debinding and sintering steps, you create residual carbon in the matrix. And for instance, for titanium 6-4, you would create titanium carbides in the microstructure, and that would create brittle sections, and then you would not get the ductility of the material anymore. But that's why it's really good to really focus on one class of material. And we could show with partner MedShape in Pforzheim, Germany, that we can really achieve nice results with stainless steel as well. So to sum up, what are the advantages of our lithography-based metal manufacturing process? As you have seen, we can create complex green parts with a 3D printing with an additive manufacturing method that are close to the metal injection molding size range, or also to the micro-MIM or micro-MIM size range of components. So we can achieve the highest resolution in additive manufacturing processes for metals, and of course with great surface aesthetics independent of part orientation. Printing of different materials is quite easily if the physical properties of the powders are similar. But of course, it's a little bit more to it than just the printing process. You really need to consider the whole process chain, and that definitely includes the debinding and sintering. So if you think about investing into a technology like this, be aware that you need a little bit more than just the printer. You really need the furnace infrastructure, and of course, you need the expertise to handle those materials. But once again, this is true for any sinter-based additive manufacturing technology. So don't be fooled by marketing messages. Really keep in mind that there is a little bit more to it than just hit the play button. Just hitting the play button. As you have seen, the printing process, it's quite easy on our side. We have shown the video. And by the way, if you're interested in more videos on our production process and how the general process chain works, find us on YouTube. We have a couple of videos uploaded there, which you could take a look at. So how to integrate? So why is LMM, lithography-based metal manufacturing, complementary to metal injection molding? Both are sinter-based processes. Both create a so-called green part in needed binding and sintering. We have a similar range of metal powders. Also in terms of size range, we are quite similar. And we, at least with stainless steel, we have shown we can achieve comparable or similar mechanical properties and microstructure after debinding and sintering. And that's why we highly believe we have a good technology and that LMM is a ramp-up technology for a small scale manufacturing and prior to a metal injection molding production. So with this, I want to thank you for your attention